Today we're going to review continuity, and we're going to get two new theorems. The intermediate value theorem, called IVT for short, and the squeeze theorem. So continuity, this is a review from pre-calculus. In layman's terms, it means you can draw the complete graph from the left side of the graph to the right side of the graph without lifting up your pen or pencil. That means your function is continuous. So there are no holes, no vertical asymptotes, no jumps. Horizontal asymptotes are perfectly fine, but no vertical asymptotes. Okay? Jumps you would see in piecewise functions and in step functions, things like that. And then no holes. All right, so a rigorous definition of continuity. F is continuous at x is equal to a if and only if the limit as x approaches a from the left on the function is equal to the limit as x approaches a on the right of the function, and those are both equal to the value of the function at a, so f at a. Now, I could combine these two. These two could be combined, right? Because saying that the limit from the left is equal to the limit from the right, that means that the limit as just x approaches a, the overall limit, those are both equal to then the limit as x approaches a, correct? So we could abbreviate this rigorous definition to just say that. The limit is equal to the value of the function. The limit from the left is equal to the limit from the right, and the function is, the value is right there as well. Okay? All right. That's the rigorous definition for continuity. So, anytime we are asked to prove or show that a function is continuous, we must do this. Okay? Alrighty. There are two types of discontinuities, removable and non-removable. A function has a removable discontinuity wherever it has a hole. So when you hear removable discontinuity, I need you to think hole. Okay? A hole is also called a point discontinuity. It's discontinuous just at a point. So the rigorous definition of a removable discontinuity would be that the limit from the left is equal to the limit from the right, but the value of the function is not the same. So the limit from the left is equal to the limit from the right, but there's a hole there. Maybe the function does not even exist there, or maybe it's located elsewhere. So for some reason, either of those situations, it would still be a removable discontinuity, a hole. All right? Next up, a non-removable discontinuity. Non-removable, then, are the other two types of discontinuities. They are your vertical asymptotes and your jumps. Okay? Non-removable. So, a non-removable discontinuity, the two one-sided limits are not equal to each other. Okay? Either they have a jump, or one of them is infinity or negative infinity. At least one of them is infinity or negative infinity. Okay, a vertical asymptote is also called an infinite discontinuity, and a jump is also called a jump discontinuity. Alrighty? With a non-removable discontinuity, the limit does not exist. And again, I said this yesterday, if even one side of a limit is infinity or negative infinity, the overall limit does not exist, even if only one side is infinity or negative infinity. All right, some examples. Number one, for what value of x does f have a discontinuity? So any discontinuity. So that means a hole, a vertical asymptote, or a jump. Well, in a function, in the equation of a function, where do we look for a hole or a vertical asymptote? We look in the denominator, don't we? The values of x that make the denominator 0 will cause either a hole or a vertical asymptote. Both of those would make it not continuous. So x is equal to 0, x is equal to -7, and x is equal to 4. All of those would be either a vertical asymptote or a hole. It does not matter what's up here. It doesn't matter whether this is a hole or a vertical asymptote because both of those would make a discontinuity. Correct answer here is C. Number 2. Which of the following is continuous at x equals 1? Is continuous at x equals 1. So I have a couple of piecewise functions defined, and then I have a regular function defined. I might just go over here because this is the easy one. I can look in the denominator, and I can tell you that g is not defined when x is positive or negative 1. And if g is not defined at 1, it's not continuous at 1. So this is not continuous at x is equal to positive or negative 1, but not negative 1. So not continuous. So I'm not going to include 3. So anything with 3 in it, I can omit here from my choices. Okay. So from the remaining choices, I know that one of them is going to be continuous and one of them is not because, or neither of them are because of the remaining choices, correct? Okay. Alrighty, so over here, alright, well if I were just doing this myself, I would come over here and do this one first, because it's going to be your easier one. There's, just the way this piece is defined, both these pieces are very simple. This is defined to be something, a rational function. The rational function, I'll go ahead and do this first. A rational function, I would go ahead and factor and see if I need to reduce it. So that factors into x minus 2, x minus 1 on top, and on the bottom we have an x minus 1. And since, and only since, x is not equal to 1, I can reduce these. Since x is not equal to 1, I get to reduce these, and that becomes, so this becomes just x minus 2. So it's like there's an x minus 2 sitting here instead of this rational function. So I would go ahead and plug 1 into that x. 1 minus 2 is negative 1, so my top piece is negative 1 when x is 1. Okay? Well, when x is not 1, I guess. It's approaching negative 1 from both sides. Now, if I do the same thing on the bottom, there's no x over here, so this piece is 1. These two do not match. So this ends up being a line that approaches, when x is 1, the y value here is negative 1. But so there's a hole there, and it is not filled by this one. This one is up too high for it. So this is not continuous. So I know my answer here is going to be, well, either 2 only or none. But this one is going to be really quick to find out, because I can just put this 1 in for the x here, 1 in for the x there. Half of 6 is 3, plus this 1 is 4. And 5 minus 1 is 4. These match. So H is continuous at x equals 1. Okay? All right. So a couple of multiple choice questions give you an idea what those can look like. Here's another one. Here's f of x. I need to put a little equal sign in here. I will do that on your sheet before you get it. Okay, here's f of x is defined to be this piecewise function. I notice the k's in here. What value of k makes f continuous? I'm going to do a similar process to what we just did. I'm going to put this 1/4 in for the x's. 1/4 in for the x's, and f will be continuous if the two pieces are equal after I put 1/4 in for the x's. So 1/4 cubed is 1 over 64. I'm going to go ahead and multiply that by k, and I'll have k over 64 for that piece right there. Minus k over 4, minus that 1/4, and that must be equal to 16 times 1/4 squared, that's 16 over 16, minus the 2 that's sitting here. Okay? I'm looking for k here, so I don't like having the fractions. I'll get rid of fractions as soon as I can, usually. So I'm going to multiply both sides by 64, and that will get rid of all my denominators. I'm left, and I'm distributing, so I have a k left from this piece. 4 goes into 64 16 times, so that's 16k minus 16 is equal to, this is negative 1, times 64, negative 64. So I have negative 15k is equal to, I'm going to add the 16 to the other side, and now I'm dividing both sides by negative 15. So we get 48 over 15. 3 goes into each of those. 16 over 5. C. Alrighty. Number 4. The graph of g, a piecewise function, is shown on the right. Which of the following statements is false? Got to be careful with that. We want the false. So I like to, on each of these, I will write true or false. Okay, so for the first one here, g has a non-removable discontinuity at x equals negative 1. Non-removable. That means a jump or a vertical asymptote, because removable is a whole. So non-removable is the other two. So at negative 1, when x is negative 1, we have a whole. That's a whole. So this thing is false. Number 1 here is false. Okay, number 2. G has a non-removable discontinuity at x equals negative 6. So again, jump or vertical asymptote at negative 6. So I'm going to go to negative 6. I go to my two pieces, and indeed I do have a jump. So this one is true. G does have a jump at negative 6. So G has a non-removable discontinuity at x equals negative 6. Okay, one more. G has an infinite discontinuity. That means a vertical asymptote. An infinite discontinuity at x equals negative 7. I go to x equals negative 7, and sure enough, I do see a vertical asymptote. This is true. So the only one that I want to keep here is the only false one, number 1, so A. Alrighty. Doing good here. Number 5. I just wanted to give you, you will see these as, most likely, you'll see these as multiple choice questions, so I wanted to give you a variety of examples on that. Okay, given this piecewise function, which of the following statements is true? This time we want a true one. Okay, f is continuous for all values of x. F has a jump discontinuity at x equals 4, a point discontinuity at x equals 4, an infinite discontinuity at x equals 4. Let's find out. I'm going to plug 4 in for all the x's, for both the top piece and the bottom piece. So this is 16 minus 8 plus 3. That's 8 plus 3, which is 11. And this one is half of 16, which is 8, plus 4 minus 2. That's 12 minus 2, which is 10. So on the left, look at how they told us. On the left, we're approaching 11. On the right, we're approaching 10. That's a jump. Piecewise functions can be defined in different ways, either like this with left and right, or on the other page we had a piece that was defined differently, like this. This means that f is equal to this everywhere except x equals 1. Everywhere except x equals 1, right? At x equals 1, the function value is 1. So if I were graphing this, I would immediately go to when x is 1, y is 1. And then I would graph this piece. We have x minus 2 everywhere except x is equal to 1. Everywhere except x is equal to 1. That's why we had a hole there, okay, that was not filled with the function. Okay, so those are the two different ways that you can be given piecewise functions. I know that people, when you first start this class, you're not totally comfortable with piecewise functions. By the time you leave this class, you will be much more comfortable with piecewise functions because you're going to see them quite a bit. Okay, number 6, show that f is continuous at x equals 0. Show means you must prove it, all right? So we have to use the rigorous definition of continuity. The rigorous definition. We need to show 3 things. Piecewise function. I need to show that the limit as x approaches 0 from the left is equal to the limit as x approaches 0 from the right, and that is equal to f of 0. That's the rigorous definition, so that's what we have to do. They are telling us to show that it's continuous, so these are going to be equal, okay? All right, from the left, I come up here, okay? I am going to go ahead, before I take it over here, I'm going to go ahead and factor this. So I can go ahead and factor this. X times x plus 4 divided by, I'm going to take a 2x out, and I'll be left with 2x plus 1. And because x is not 0, I can reduce these x's. They reduce to 1. So I am left with the limit as x approaches 0 from the left of x plus 4 over 2 times 2x plus 1. Okay? I can put 0 now in for x. I'm putting 0 in for x, and I get 4 over 2, which is 2. Okay? Next piece. When I put 0 in for the x's here, what do I get? In fact, I could even write that down. 0. This is also equal to 2, as we expected it would be. And what is f of 0? Well, f of 0 uses the same rule that we just used for this piece, and that was already 2. Okay, so now I can write the limit as x approaches 0 from the left of f of x is equal to the limit as x approaches 0 from the right of f of x, and that they are both equal to f of 0. Therefore, f is continuous at x equals 0. You guys, math calculus is very logical, okay? I want you to see the logic here. The limit from the left is equal to the limit from the right. It's equal to the value of the function, right? Therefore, f is continuous. It's very logical. I think you'll see all year long, if you go into this with that mentality, you'll realize just how easy calculus is. Calculus to me is logic and recognizing patterns. Okay? All right. Okay, let's now talk about the intermediate value theorem, IVT. The IVT is an example of an existence theorem. Okay? We are going to get 3 existence theorems in this course. This is our first one. Okay? This type of theorem guarantees the existence of something. In all 3 cases, it guarantees the existence of a value of x. Okay? So, before I get into that, I want to make this make sense to you because IVT is extremely logical. If Susie weighed 7 pounds at birth and at 17 years old she weighed 137 pounds, must there be an age at which Susie weighed 86 pounds? Well, of course. Okay? My first part-time job paid $3 an hour. I am making that up. I don't remember what my first part-time job paid. I think it was less than $3 an hour though, but for our purposes here, I was paid $3 an hour. Her 4th part-time job paid $4 an hour. Must there have been a part-time job that paid me $3.25 per hour? No. And in class, we would talk about why not. Why did we say yes to this? 86 was between 7 and 137. 325 is between 3 and 4. Why was this a yes and this is a no? And hopefully it wouldn't take too long before you would come up with the concept of continuity being crucial here. Okay? Weight is a continuous function. Pay is not, right? So for IVT, we must have continuity of the function, okay? And there's nothing magical about that 86. We could have said 96. We could have said 106. We could have said 42, right? We could have said every weight between 7 pounds and 137 pounds, right? Now, must there have been an age at which Susie weighed 140 pounds? From this information, no, not necessarily. Could there have been an age where she weighed 140 pounds? Yes. Okay. So the intermediate value theorem, IVT, is what I call the in-between or the intermediate in-between theorem. Okay. And continuity is the basic condition for IVT. Here is IVT in a formal way. If a function f is continuous on a closed interval, this is the minimum that it must be continuous. So, on this closed interval, it would be age 0 to age 17 years. 0 to 17. It's continuous. And if f of a is not equal to f of b, so the two y values are not equal, and if k is any number between those two y values, k is like the 86 in our example, the 86 pounds, then there must be at least one number c between a and b such that f of c is k. C is your x's. In this case, it was your age. In this case, it was the age. There must be an age between 0 and 17 years at which Susie weighed 86 pounds. Okay? The IVT guarantees that every y value between f of a and f of b must exist for some x value between x is a and x is b as long as f is continuous. Okay? Now, a couple of sticky things here. We must have continuity on a closed interval. We must have continuity on the closed interval. This is something that kids forget. Continuity must be on the closed interval, and this value of c must be in the open interval. C must be in the open interval, not outside the interval, and not at the boundaries of the interval. It must be inside, okay? This is the thing that kids forget right here, that C has to be between A and B, but not equal to A or B, all right? Okay, let's look at an example. The most common way I think you would see this problem is in an FRQ, where you're given a table of values, okay? And they give you information at the start of the problem. So we are given that h is continuous here, and that h represents the height of the tree at time t. H of t is in meters and t is in years. Selected values of h are given in the table above. I'll correct that on your sheet. Explain why there must be some time t at which the height of the tree is 17 meters. Okay, so AP and I am very particular about how I need you to answer this. I need you to say 3 things, and I am going to note those 3 things with a bullet point. Okay, 3 things. If you want to label them 1, 2, and 3, fine. I like to use bullet points usually. All right, number 1, I need you to restate, in this case restate, the basic condition. The basic condition is that I need for h to be continuous, specifically on the closed interval from 1 to 10, or whatever I'm going to be using, okay? Now, in this particular example, I need to explain why there must be a time where the height of the tree is 17 meters. At time 1, the height of the tree was 0.7 meters. At time 10, the height of the tree is 27 meters. 17 is between those, true? So I could use from time 1 to time 10. But 17 is also between 0.7 and 21.2, or 0.7 and 19.3. So I could use from 1 to 10, from 1 to 7, or from 1 to 6. I could not use from 1 to 3, though, because 17 is not between 0.7 and 3.2. I could use between 3 and 6, because 17 is between there, or time 3 and time 7, or time 3 and time 10. I have some choices here, okay? I'm just going to pick the outside ones because I want to, but it doesn't matter, okay? So I need you to say that h is continuous, okay? Specifically, h is continuous on the closed interval 1 to 10, okay? Since h is given to be continuous. Now, before I leave that statement, I know I'm spending a lot of time on this, but before I leave that statement, I will tell you that since they gave us h is continuous, that means h is continuous everywhere. So did I really need to say on this closed interval? No, I did not. I could have just said h is continuous since h is given to be continuous. I could have said that, all right? because continuous everywhere includes 1 to 10. All right? So in the future, that's pretty much what I do. I just say, if they tell me that it's continuous, I just say H is continuous since H is given to be continuous. You need to state this, and you need to say why. All right? Okay, that's the first one, and I call that my basic condition. Alrighty? When we do our next existence theorem, you guys, we're going to have the same steps. Still 3, and the first one is the basic condition. So I'm getting you guys used to doing that. Alrighty? Okay, the next step I call my meaty math step. Okay, this is where the numbers come in. All right, I want 17 to be between two numbers, so I'm going to say H at time 1 is 0.7, H at time 10 is 27. And now I need to make a statement about 17. I need to say that 17 is between these. (17) is between those values. Okay? That's my mathy step. It's all numbers. Well, a couple words. Okay, this is the way I like to do it because I think it makes the most sense to most of my students. However, I would be remiss if I did not give you a more abbreviated way to write this in case you prefer it. Alrighty? We could say that H of 1, which is 0.7, is less than 17, but 17 is less than H of 10, which is 27.0. Okay? This is another way to say that 17 is between these two values. Alrighty? Now, I know you're going to ask this, Miss Murray, do we have to say H of 1 and H of 10? Could we just say 0.7 and 27? No, you can't. You can't. Alright? Miss Murray, could I just say H of 1 and not say the 0.7 and H of 10 and not say the 27? No, you can't. And I hear this all the time. But Mrs. Murray, it's right there in the table. Why do I have to write it? Because AP says you have to. All right? And if AP says you have to, Miss Murray says you have to. Got it? So, if you want to use this abbreviated version, do it. If you want to write it like this, do it. I will keep writing it like this because, again, I think it makes the most sense to my students. The most sense to most of my students. All right. The last step is my conclusion. And boy, do kids tend to have problems just writing the conclusion. But here's my best advice to you. Go to what they said to do. Here's what they said to do. They said to explain why there must be some time t at which the height of the tree is 17 meters. Go to that sentence. Get rid of the explain why and rewrite everything that comes next. And you'll always get your conclusion. Alrighty? There must be some time t at which the height of the tree is 17 meters. Okay? And you will never get your conclusion step wrong if you do that. Alrighty? Rewrite this verbatim and you'll never get it wrong. However, since we're here and I'm giving you guys a couple of abbreviated ways to write things, okay? There is an abbreviated way that we could write this. And I'm going to write it for you. There must be That's a symbol for there must be, there are, there is. Sometime t, at which the height of the tree is 17 meters, h of t is 17. That is the abbreviated way to write what I wrote in blue right there. Okay? These are some conventionally used mathematical symbols. This is the existence symbol. That means there is, there are, there must be, is, are, be, those existence verbs, okay? That's the symbol for that. You know, we have T in the problem. This is the symbol for such that, or at which, things like that, okay? So, if you want to use those two symbols in place of some words, that's fine. You certainly do not have to. I will keep writing it out in words, okay? Every once in a while, I will kind of make a mistake and not make a mistake, but I will use these symbols just out of habit, all right? We're going to be writing a lot of words in this class, okay? And having some conventionally used mathematical symbols to represent words is convenient, all right? So you'll see some of those from time to time. And I'll give you more of those as we go on. Alrighty, so let's do another one. I won't talk quite as much with this one, I promise, maybe. Okay, a customer is at a gas station pumping gasoline into a gas tank. The rate of flow of gasoline is modeled by a differentiable function, f, where f is measured in gallons per second and t is measured in seconds since pumping began. I got this from the 2023 AP exam, FRQ. Selected values of f of t are given in the table. Explain why there must be a value of c in the interval from 0 to 150 such that f of c is 0.12. Okay, I'm looking here. Okay, they say to use between 0 and 150, but f of 0 is 0 and f of 150 is 0. And 0.12 is not between 0 and 0. So even though they gave me this, I need to use my logic and go inside of that given interval, right? So let's find an interval where 0.12 must lie. I could use 0 and 90. I could use 60 and 90. I could use 90 and 120, or I could use 90 and 135. Any of those, okay? I think I'm just going to use 0 and 90. All right, so I first have my basic condition. I need to say that f is continuous, specifically on whatever boundary that I need it to be. But they told me that f was differentiable. And again, I am using what we learned in pre-calculus here, but if f is differentiable, then f must be continuous. Not just on an interval, but everywhere, right? So I'm just going to leave it that f is continuous. This time I'm not going to state a specific interval, because I don't have to. If it's continuous everywhere, then it's continuous on the little interval that I need it to be on. So f is continuous since f is given to be differentiable. Okay? Basic condition. And you say what it was given to be. You do not say that since f is given to be continuous, because f was not given to be continuous. F was given to be differentiable. So don't tell me that it's given to be something that's not given to be. Okay? All right. Step 2, the meaty math step. F of 0 is 0 f of 90 is 0.15, and 0.12 is between these values. Therefore, so, oh, there is an abbreviation for so also. It's this one, or you can use the little arrow with the double bar on it. Okay, but I just usually write so. So, okay, I go up to my sentence here, get rid of the explain why, and rewrite verbatim everything else. There must be a value of C in the interval 0 to 150. 0 to 90 is inside 0 to 150, so we can just say 0 to 150, or we could have said 0 to 90, either one, alrighty? Such that f of C is equal to 0.12. Okay? In the abbreviated way, I would say, so there must be a value of C in that interval such that f of C is 0.12. That's the abbreviation way. Alrighty, next up, and last for today. It's a long day for the lesson. Okay, the squeeze theorem, also known as the sandwich theorem. You use whichever you like. I tend to use squeeze. You can use sandwich if you want. This is another very obvious theorem. If f is continuous and the graph of f lies between two other graphs for all x in some interval containing x equals c, except possibly at c itself, so there might be a hole there or something like that. If the limit as x approaches c of g is equal to the limit as x approaches c on h, then the limit as x approaches c on f must be the same value, okay? So let's think about that. Here's visually what it would look like. We have some graph, and I'm going to call that G. I have another graph, and I'm going to call this one H. Notice how I said that they meet somewhere? I know they must meet somewhere because they have the same limit as x. At x equals c, they have the same limit, so they must be going to the same spot, okay? Except there could be a hole there, but we don't care. F comes along, and I tell you that F lies between those two. So I don't know what F is doing, but F lies between those two. And if F lies between those two, it must be sandwiched or squeezed between them right there, right? That's what I mean by the squeeze theorem or the sandwich theorem. It must be in there, okay? You will see these as multiple choice questions, okay? All right, this multiple choice question. I give you a function g. I give you a function h. And I tell you that f is not given, but it is known that f is continuous, and either f is between g and h this way or the other way on the domain of f. Okay? So f is between these two functions. We want to evaluate the limit as x approaches 1 of f. Okay, when you are given this guy right here, they are telling you what to do. Find the limit as x approaches 1 on g and h. They should be the same, or our answer is D. They are either the same or our answer is D. I'm going to find the limit as x approaches 1 on g. That will be -1. I'm going to find the limit as x approaches 1 on h. If I put 1 in for x, I get a -1. So, the limit as x approaches 1 on f must be the same thing. That's the squeeze theorem. Do one more quick one. All right. If h is continuous, and it is known that on the interval from negative 2.9 to 2.9, the graph of h lies between the graphs of f and g. Evaluate the limit as x approaches 2 of h. So it's telling me what to do. I'm going to find the limit as x approaches 2 of f. I'm going to find the limit as x approaches 2 of g. And either they will be the same value and I'll get one of these answers, or they'll be different values and I will get D as my answer. Okay? So for f first, I'm putting 2 in for x. And I'm going to get sine of 2 and 12 will reduce, and that's pi over 6 plus 5. Sine of pi over 6 is a half, and 1/2 plus 5 is 5.5. For g here, I'm putting 2 in for x. I'm going to have 4 over 4, which is 1, 2 over 4, which is a half, plus 4, and that is also 5.5. Therefore, the limit, that was a sloppy therefore the limit as x approaches 2 of h must also be 5.5. Okay, a big day today, lots going on here, continuity, IVT, and the squeeze theorem.